Hello everyone. Um, this is our module 4 and we are starting week 4, right? Can you believe that we are starting week 4? Halfway there, okay? And module 4 is, we are focusing on chapter 7. Chapter 7 is, we are going to look at work, energy, and at the end you can read about the energy resources. Here I am focusing on mainly what is work, how work and energy is related in this lesson, and the second lesson I can go over conservation of energy. Okay, what do you think? What is work? Okay, in science this is something different from what we do every day. We go to work, we work at home, work, right? We are tired of work, school work, but this is not the one we are doing every day. We are going to look at in scientific eye what is the work. It has a different definition. We are going to look at that, and then at the end we are going to look at what is the relationship between work and energy. They are related each other. If you Google what is energy means, you would see it has a meaning of ability to do work. Ability to do work. So that tells me work and energy are related. Okay. All right. So let's look at here for this example. These people are trying to move this wagon or truck or van or anything. Okay, what do you think? Are they doing any work? You feel like they are doing work, right? You're pushing this really hard. Or you can try to push your wall in your room. What do you think? Are you doing any work? Okay, based on the definition, work is defined as, if I look at here, work is done on a system. You are applied some force, there should be some kind of force, and this force should result in some kind of displacement. Your object should, in other words, move. And here, if it is not moving, even though you feel tired, this according to this definition, work is you are not doing any work. Okay, and in other words, to do work you need to apply some force, so there should be some kind of force, and this, because of this force, there should be some displacement. It goes from here to here. If I look at this one, or if you remember something from high school, in high school what we do is we define work as force times displacement. Force times displacement. This is correct. I can say this is wrong. Okay, and that's what you see, right? Work is force times displacement. But I need to be more specific here, and because in next slide I would say more specific definition. This is correct, but it is not the general definition. Okay, and look at that. You are applying a force in this diagram. This is my force, and force and displacement, look at that, acting in the direction of the displacement. In other words, this whatever the force, and you are looking at displacement and force should be parallel to each other or in the same direction, acting in the direction of the displacement. That is the a complete definition, I would say. Okay, so let's look at what should be the units for work. Force, I measure in terms of, what is the units for force? Newton, SI units. Displacement, remember displacement is different from what? Distance, right? Displacement is final position minus initial. Displacement also you measure from meters, length, Newton meters. And instead Newton meters, nothing wrong with this. We have one word for that, 1 joules. Newton meter is equivalent to 1 joule. Okay, and you would see in terms of Newton meters or joules. And work is a scalar quantity. A scalar quantity. Okay, but we know it should be parallel to each other, but work does not have a direction. Scalar means it has only the magnitude. Okay, and I think next slide, this we have this here, what I just explained. It's this physicist named Joule we use for units. Okay, what are the other units? It is not joule is the most common one, but if you measure force in terms of dyne and length in terms of centimeters, this you would see erg. It is not a common use of unit for the work. Okay, and but here we measure length in foot, and if you measure force in the pound, then foot pound, and this is the conversion factor. Okay, all right. So now I need to give some. Okay, this we talk about, right? Work is a scalar quantity. Can work be positive or negative? Okay, work can be, we will see, work can be positive, work can be 0, work can be negative. And work is positive when the force and the displacement are in the same direction. In other words, force is a vector force and the displacement are in the same direction. You are doing a positive work. On the other hand, let's say your force is this way. We'll look at the examples later. And displacement is other way. Force and displacement are opposite. In that one, you get a negative work. Okay. Also, how do you get 0 work? When you would get 0 work. So there are some possibilities, we'll look at that, but you could say if you push it, my very first slide showed that, right? You apply a force, but it is not moving, or there is no displacement. Then you would write your work as 0 when there is displacement 0 or no net force. Force is 0. But there are other conditions too. We'll look at those in a minute. Okay, before that, so let's look at here. What is the work done by gravity? Gravity, that means I am looking at a gravitational force. Okay, gravitational force, which is, we know, I could use Fg or gravitational force, which is equal to mg, right? We know gravitational force is always vertically down. Now it says what is the work done by gravity. You have an object, right? Okay, let's say it's a brick and of 2 kilograms, and you bring it down or you drop it 10 meters. Okay, all right. And what do you think? First of all, let's see my work done is positive, negative, or 0. Now we know this is the gravitational force Fg. Fg is equal to mg. You can do the math. then and it goes in the same direction as your gravitational force, then what you know, your force or work done by this gravitational force should be positive, because it is in the same direction. We talked about this in the previous slide. And I could find out work done would be then mg times, because in this case these are parallel, okay, and times displacement is 10 meters, okay. M is given to G is 9.8, 2 times 9.8 times 10. So that gives you the, I believe you get something like this, right? Okay, Newton meters or joules. Okay, now what happens here? You lift something. You lift something and it's still asking, not you are doing work, it's asking the work done by the gravity. Now still I can't change the direction of the gravitational force. It is always vertically down, gravitational force. Now look at that. Gravitational force is downward, brick is going upward. These are in the opposite direction. Therefore, your work done by gravity in this case is negative. You would get same number but negative 196 joules. Okay, now you can look at this, what happens. It's the same story. But let's look at here, right? You can read this. It's the same thing I just explained. Okay, now let's look at more general case. And now in this case, look at this. Okay, this is the most correct definition. The work done is FDF. Earlier we saw that work done is F times D, but that is it validates for special special places. But here the work done by a constant force is defined as distance moved by multiplied by the component of the force. This is important. Force in the direction of displacement. So let's look at here and see with the diagram. And if I draw the same diagram here, I'm doing the same thing. So you are, there's thread or rope or something, okay, and that means it could be a tension force, or you just apply a force. Now not in the, right, this is the force, this is the displacement. Now what we do? I can do FD. Why? I didn't define work as F times D. I define work as F times D, but force under one condition. Force and displacement should be parallel to each other in the same. Okay. And now let's look at here. How can I make this work? I know, if I know this force, I can look, because this force is in 2D plane, right? Okay, but there is a force component here. We call this is Fx, so this is Fy, and Fx is cosine theta is, I know F because I have right triangle, Fx over F, or Fx is F cosine theta. So that solve my problem. Look at that. Now if I look at my Fx and this displacement, both are parallel. Therefore, I could write my work done is Fx times D cos, that is F cosine times D, or I can write this as Fd cosine theta. Okay, and if I write in this way Fd cosine theta, this is the work, And cosine theta, the theta is the angle between force and the displacement. But make sure when you put these two tails together, because this is a vector, we know a vector, this is the, we call head tail, right? Head tail or tip tail. And these two tails are together, then this is the angle between force and displacement when you put the two tails together. Okay, so that's important. Now let's look at here. Now we have the nice definition, which is F times t times cosine theta is equal to my work done. Okay, now I can look at the angle and I can decide my work is positive, negative or zero. Okay, so let's look at here. And this is right a small angle. My angle is less than 90 degrees. Any angle 90 degrees you would get a positive number. But what happened here? This is your force. Whatever the force is perpendicular to the distance. Check your calculator and cosine 90. If theta is now these are perpendicular, then my angle is 90. Cosine 90 is 0. Therefore, you would get a zero work done, because it doesn't matter how big your force, what is your displacement. If this is 90 degrees, work done is 0. Here, if your angle is greater than 90 degrees, you can check. Maybe theta is 120, cosine 120 is a negative number. Okay, and if it is something like this, this is the displacement. Okay, this is the force. Now what is my angle? This is theta 180 now, because remember I define theta as angle between F and D when two tails together. See, two tails together. And theta 180, so that cosine 180 is, check your calculator, gives negative 1. So that means you would get a negative number. Okay, this is the best way to look at, an easy way to look at, mathematical way to look at the angle. Okay, let's do a couple of problems. And this slide shows that how to do this kind of problems. First, draw a free body diagram means actually what you do, you draw all forces acting on your object. Draw all forces on object. Okay, whatever the object you are. And this is really important. Choose the coordinate system, because you need to tell me which way is positive, which way is negative. There is no rule, but most of the time you would see I am taking this, going to the east as positive, going to the north as positive y. Okay, and we look at the work done. Okay, let's do some examples. Okay, the lady in the figure exerts a 60 Newton force on the box, pulling 35 degrees. And how much work she does in pulling the box 40 meters? Okay, 45 meters. So box goes from here to here, and it's not, make sure work done is not just force times. If you put this one, this is incorrect. Okay, why? Remember that force and the displacement should be parallel to each other. Previous slide we saw that it should be FD cosine theta, because then I'm looking at this component, right? Okay. And now what is my angle theta? It's in this problem it is straightforward. Angle is given 35 degrees. So that gives me 2200 joules. Okay, it follows everything. See, two tails together, and I know the theta. All right, that's very simple one. Let's look at here. Okay, what he does while doing, he pulls the canister vacuum cleaner with the force of, okay, this is the force, 55 newtons. It says 55, angle 30. He moves the vacuum cleaner distance 3 meters right now. Okay, look at this. Calculate the work done by all the forces acting on the canister. Okay, and now let me instead messing up this slide, so let me insert a new slide. Okay, I'm not going to draw canister, but I could draw some object, right? So let's draw. It doesn't matter. This is my canister. Okay, what we have, I need, this is the one, it's moved. It says what's the distance it moved? 3 meters. It moves 3 meters, and this person is applying a force of 30 degrees, 55 newtons. Anything else we know? Okay, and what else? Now if I look at this, this is the canister moving on, right? Let's assume this is a smooth surface. If we have friction, I need to take care of that too. Assume this is frictionless. Okay, we can do that with the friction too. We'll look at that. Now, anything else here? What are the other forces acting on? We know it has a mass, therefore we have gravitational force, Fg. Anything else? We have normal force, right? Because it is on a surface, therefore we have normal force. So this is my normal force. Remember, normal force is the force that surface pushes on the object. Okay, now it's asking find out all force work done by all forces. But I know this is the only thing I should know, right? Work done is Ft cosine theta. Let's do one by one. Work done by gravitational force, Fg. Work done by gravity would be gravitational force mg, displacement 3 meters. What is my cosine now? What is the angle? How do I take that? This is the gravitational force, this is the displacement. See, it's 90 degrees, right? So that is the most important part, because this is my displacement is this way and gravitational force is here. So therefore this is cosine 90. Cosine 90 is 0. Therefore in this one, gravitational force is not doing any work, because your force is perpendicular to the direction. How about the normal force? If you want, if you don't like, you can put the negative 90, that's fine. Cosine negative 90 is 0 as well. Work done by normal force. Normal force F, D is still 3 meters. Cosine, what is this is the force, and I'm not looking at here, this is my displacement, right? And I'm looking at what is the angle between force and the displacement. Again, this is 90. So therefore this is 90. Normal force is not doing any work either. Okay, who's doing this work then? This whatever the applied force. You can do that. Work done by applied force would be, force is 55 newtons displacement is 3 meters, cosine. Now this angle is 30. You can do the math. Okay, so see, it's pretty simple. Oops, what happened? Okay, so that gives the my work. Okay, and you will end up with 130. Okay, similar problem. Let me read the problem and let's do it in a different slide. Okay, you have a 50 kilogram. Write down or highlight or note down everything, whatever the given information. You have a 50 kilogram crate. You move it 40 meters and you are applying 100 newtons, 37 degrees. Okay, now the difference is the flow is rough and exerts a frictional force of 50 newtons. Determine the work done by each force acting on here. I hope I remember 50 kilogram and 40, and let's try. Insert new slide. Okay, right. I have a, before I forget, just put at the numbers. I have a 50 kilogram crate and you are moving it 45 meters, I believe, and you are applying 100 Newton force, 37 degrees, and in addition 100 newtons, 40 meters. Okay, and this is a rough because this matters. This matters because all right, now let's figure out the other forces. Okay, the easiest one I would draw gravitational force mg, and this moving on here we have normal force, and now anything else, it has a friction, therefore there's a frictional force. Which way is the frictional force? The frictional force is always opposite to the motion. Remember that last module in week 3, frictional force is opposite to the motion, parallel to the surface. So this is my frictional force. I believe frictional force is given 50 newtons. Okay, once you have, this is my we call this free body diagram, FBD, or free body diagram. Once you have this, you can forget about the physical picture. Okay, now it's asking me to find out what is the work done by all forces. A net force means total force. I could do that work done by gravity, gravitational force first. Second, work done by normal force. What else? Now we have work done by applied force, which is with 100 newtons, right? And the fourth one, now we have new one, we need to find out work done by friction as well. Okay, and how do I find that? Any force, work done by any force, FD cosine theta. This is my equation, and just plug it. I don't mind, I'm not trying to find out the normal force. Displacement is 40. Cosine, it's the same story, right? 90, because here normal force is perpendicular to the distance. So that's why I didn't worry about to find out the normal force, because I know this is 0. Therefore, normal force is not doing any work. How about gravity? Gravitational force mg, displacement 40 meters, again here cosine negative 90 or 90, because see here, gravitational force and the displacement. In this case, this is also 0. Applied force. Here 100 newtons. FD is 40 meters. Cosine 37. Now it is doing work. How about friction? Frictional force is given 50 newton, 40 meters. Now your job is to figure out what is the angle. Okay, let's only look at frictional force. This is my okay. So let's try. This is my instrument. Okay, this is the box, right? I don't know why it's not good. Let me go with the black. And this is the box. And okay, so this is, I'm trying to move it to 40 meters. And now my frictional force is this way. And this is my displacement if I draw as a D. Now what is the angle? Looking at this angle, which is 180. 50 times 40 times cosine 180, you would get negative 2000 joules. Cosine 180 is negative 1. Okay, now we have everything. You can put check the numbers. I calculated everything here, and you are ending up with here. Okay, because gravity is 0, this 0, frictional force get a negative number. This is the applied force. Okay, therefore if I want to find out the net force, you would have to add everybody. All right. Okay, you can do this one for practice, and you will see similar problems in your homework assignment or web assignment too. Okay, this is pretty straightforward and it's very similar to previous two problems. Okay, the catcher stops a 90 miles per hour pitch. Okay, and positive work, negative work, 0. Okay. Okay, ball comes in this direction. Okay, you are here. I'm not going to draw my hand or thing because my drawing is not going to be nice. And anyway, ball is coming in this way, right? This is the direction of the displacement. You catch it, you apply your force in this way, and force and the displacement are opposite. So therefore, you know, it should do the negative work. We did it very early. Okay, and actually this is pretty simple, I would say, if you understand or if you apply the equation for the definition correctly. Because for our class we are not doing anything, something is moving in inclined plane, that is somewhat I didn't see any problems for your homework, therefore I don't have to talk about here to what I'm looking at, something like this, at something is moving in inclined plane. Okay, all right, let's because I mentioned that we are going to look at the relation between work and energy. Okay, but before that I need to introduce two terms: kinetic energy and the potential energy. Okay, and this week discussion board is about the potential energy, which I will be doing for the second lesson. Kinetic energy is defined, or it is a type of energy. It's associated with the motion. So what that means is energy is with motion. That means if something is moving, we have this type of energy. It's a scalar quantity. Energy does not have a direction, and therefore it's a scalar. And energy has the same unit as work. That's why right, that's another way we could say these are related. Okay, at the end of this lesson we are going to look at how work is related to this energy. Okay, and I am skipping the derivation because for our class it's not complicated, but textbook does not explain it, and I thought, okay, just give you the result how work and energy are related. Okay, and mathematically this is defined as kinetic energy is defined as half mv squared. Half mv squared. M is the mass, v is the speed. Okay, and half mv squared, and units is joule, but I could look at here, right? Kilogram, speed, meter per second squared. So that's why I put in terms of kilogram, meter per second, meter squared, second squared. Okay, and this kinetic energy depends on mass and the speed. All right, what do you think? When these objects move at the same speed, which will have the more kinetic energy? Pretty obvious. It depends on two things. Okay, and but here they have the same speed. They do have the same speed. So this is same. So then it depends on this mass, right? Then truck has the more kinetic energy because it's heavier. Okay, all right. So let's look at here. Small airplane moving along this one. Mass 690 kilograms and energy is 25,000 joules. What is the speed of the plane? Kinetic energy is given. We need to find out the speed, solve for speed, because this is given 25,000 half mv squared. So you get v as 8.5 meters per second. Okay, and this is just to get rough idea. And if you are walking, so you get around with mass and your speed about 50 joules. Car at 60 miles per hour, okay, it's pretty big number, then you square it, right, and you get 10 to the power 6. Okay, so let's look at here. Ball A has half the mass and 8 times the kinetic energy of the ball. What is the speed ratio? Ball A has the half the mass and 8 times of ball B. Okay, ball A, ball B. What we look at, ball, if I have m va squared, ma squared, here have mb vb squared, right? But it says half the mass, so of mb, that means I could write half mb over 2, right, because it says half the mass. And it says that 8 times the kinetic energy of the ball. So this is, right, this one mb va squared over 4, right? This quantity is 8 times half m b v b squared. So that's what it says. Okay. Now what is it asking? Asking VA to VB, right? Okay. MB, this is just the language. You are just applying this. MB cancels out because this energy is 8 times of the kinetic energy of the ball B. Now I am ending up with, what am I ending up with here? VA squared over 4 is equal to 4 times VB squared. VA squared is 16 VB squared. But I'm looking at VA to VB, then square root of 16, which is 4. That ratio is 4. Okay, it's just for fun. Okay, and the ball is moving. How much kinetic energy ball have? It's pretty simple. Part A. Have m v squared v. Okay, you can simplify. Part B, how fast must a 2.24 gram table tennis ball move in order to have the same kinetic energy? Okay, so that means it's easier to have the numbers, right? 9 times 63 divided by 31.5 joules. Okay, you can check the math. Alright, now have the same kinetic energy of the bowling ball. Bowling ball had 35 joules. Now have M, we need to look at the V, right, of the table tennis ball, TT ball, table tennis. But can I write just put 2.24? Can I do that? No. Why? Because this energy here is in joules, right? And you use kilogram meter per second square, meter square second square. And look at that, this is gram. I need this one in kilograms. How would you make it to kilogram? You need to divide it by 1000. Now it is, okay, now you can solve for V. Okay, this is important because you need to use correct units. Okay, now we are in a position where I could give you the work energy theorem. Work energy theorem tells us net work done on the object. Net work means actually total work done on the object is equal to change in kinetic energy. Change in kinetic energy is always final minus initial kinetic energy. Okay, final minus initial. I could write, if I want, half mv squared total. This is the same thing I'm writing. Half mvf squared, that is the final, half mvi squared. So this is really important because if we have velocity information, you could directly find out the total work done. Okay, and this is the same thing, but let's look at here. And if I let me introduce new slide. It gives, okay, this is my work energy theorem. Total work done is equal to change in kinetic energy, which is delta K. Delta means, remember, change in always. Or I could write half m vf squared minus half m vi squared. Okay, so let's say your total work done is positive. Okay, that tells me half m vf squared minus half m vi squared is positive, right? So that tells me your final velocity is greater than initial velocity. So that means it is speeding up. Maybe it goes from 10 to 30. Okay, and it works other way too. If something is speeding up, your total work done is positive. Okay, you could look at the other one too. If total work done negative, you get half mvf squared greater than Okay, in other words, write your final smaller than initial, so that gives you your object is slowing down. Okay, don't worry, don't be scared when you see those letters. It's just letters. Just leave it. Who cares? How about total work done 0? What that gives? So that gives you your change in kinetic energy is 0. This is really important. So that gives you VI is equal to VF. So what that tells you? If VI equals VF means this is moving with constant velocity. Your velocity is not changing, right? So that means your object moves with constant velocity. See how qualitatively how many things I can take from here. And I put the same information here. I didn't want to mess up the slide. Okay. Alright, it's the same thing. If the network is positive, kinetic energy increases. If negative, decreases, slows down. Okay, it's the same thing. That makes sense. Look at that. Positive work done on the object, speed increases. Remember, let's say apple is falling down, right? What is the work done by gravity? mg, and it's falling down, displacement same. Therefore, we know work done by gravity is positive. So that means it should speed up, right? From when we come to here, we saw that under free fall, at each second, it's gaining speed of 9.8 meter per second. Remember when we talk about the free fall. And on the other hand here, if you toss something up, what is the work done by gravity? Object is going up, you toss something up. But gravitational force is always downward and displacement is upward. Then your work done by gravity is negative. Work done by gravity is negative, so that means it should slow down, right? That's why when you toss something, what happens? It slows down and up to here. Then when it comes back again, it speeds up. We talk about this one in detail when we look at the free fall. Okay. Now let's look at how much work is required to accelerate car from 20 to 30. And now it's given the velocity information, asking me to find out the work. Because one thing I know, I can find out the work FD cosine theta. But you get stuck if you use this definition. Why? You don't know the force. Okay. You could figure out the force, but you don't know the displacement. And you could do that, but it's a lengthy way, right? You know the initial velocity, you know the final velocity, you might be able to find out, but you could directly use work energy theorem, because total work done is equal to change in kinetic energy, which is half mv squared minus half mvi squared. You know V, you know the energy, you can find out the total work done. Okay. And it's this very similar example what we did earlier. What is it asking? 30 kilogram, and you push it 120 newtons through a distance. Frictional force of 5. Calculate the net work done. Okay, and I've shown you this one. In addition, what forces we have in addition to the applied force and the friction. I do have the gravitational force mg, and I do have the normal force. but they are not doing any work. Work done by gravity is 0. Work done by normal force is 0. Okay, if you are not sure why, work done is, now I'm using FD cosine theta because I don't know anything, any velocity information to use work energy theorem. That's why I'm using this. Okay, think about, pause this video for a second and think why work done by gravity I put 0, why I put work done by normal force 0. If you don't, just go back to previous examples and figure out. Okay. Alright, let's look at work done by applied force, which is 120 newtons. I'm looking at here, right? D is 0.8. Now, what is the angle? You are applying force here, applied force. I'm looking at this one, and displacement is in the same direction. So therefore there is, see, because remember it's two tails together and they are parallel, therefore angle is 0. Cosine 0 is 1 and you are getting 96 Newton. Cosine 0, 0. But how about work done by friction? Work done by friction is, frictional force is 5.0, D is 0.8. What is the angle? Cosine 180. So that gives you negative 4. Why cosine 180? Frictional force is this way. Box is moving to the right. I'm looking at this angle. Okay. I put the numbers because part total work done, you are ending up with 92 joules. Part B is asking us to find out the initially moving point 5, what is the final velocity. Okay, whenever it's asking the velocity information, use here work energy theorem. Total work done is half mv squared minus half m. But from the first part we have the 92. I plug the numbers. I don't know why these are so small. Solve for VF and I get this. Okay, again, my only advice for you is don't watch what I am doing. Try to do yourself, and when you get stuck, come back and see what I am doing or my answers. Because if you just watch this and listen, and you will see, okay, yes, this is cosine 180, yes, this is cosine 0. But when you try to do yourself, you get stuck. You therefore just figure out, right, what are the confusing places and then go over. Okay, all right. The last part for this lesson is something called power. Okay, power is related to work. Okay, and it's defined as power is the rate of doing work per unit time, and work per unit time and joules per second, right? Work is in joules per second, and joules per second we have another unit which is watts. Okay, power. What is this? Because work done is force times displacement over time, and d over t, displacement over, let me erase this and write it again. Here, right? No, I was here. Okay, and here what I have, force is, definition is work per unit time. Work is, I am using F, force times displacement over time. Now I know this is distance over time, right? Displacement over time we call velocity, F times V. Okay, all right. And how long does it take a worker producing 200 watts of power to do 10,000 joules of work? How long? So that means I need to find out the time. And this is, if you're not sure what they are talking about, check the units. This is watt. Okay, watts means power. And work done is joules, and you can solve for time. Okay, if you look at your electric bill, I don't know your who is your provider, depends on where you live. Here in Massachusetts, we have National Grid, and for my house, right, we get the electric bill in terms of kilowatt hours. Kilowatt hours. Are you paying for power or energy? What do you think? Are you paying your electricity bill for energy or power? You can check. What I can do, I'm getting kilowatts per hour, right? Kilowatts means 1000 watts hour second. And kilowatt is kilowatt hour. So that means watt is power. So that means energy over time. Okay, so this is, okay, 10 to the power 3 watts. Watts is joules per second, right? And here you have joules per, this is hour second. Okay, second cancels out, you're ending up with joules. So that means in 1 kilowatt hour means 3.6 times 10 to the power 6 joules. Okay, so that would be 36. Right, joules, this amount of joules. Joules means energy, therefore you're not paying for power, you're paying for energy. Okay, let's look at here another example. Mike applied 10 newtons force over 3 meters in 10 seconds. Joe applied the same force, 10 newtons, over the same distance or 1 minute. He is slow. Who did more work? Mike or Joe? What do you think? It's asking who did more work. Remember, work. Work depends on only force and the displacement. Depends on force and the displacement and the angle. In this case, they are in the same direction, and force and displacement are same. Doesn't matter who finish first, they both do the same work. But if it is power, you can figure out who did the more power, right? Okay. And let me stop here. In lesson 2, I will start talking about potential energy, other type of energy, and we'll talk about conservation of energy. Energy is conserved, conservation of energy. Okay, go over this and let me know if you have any questions. All right, let me stop sharing.